All right. Got everybody's homework. Today, we're gonna, like I said, we're gonna go to the observatory after I talk a little bit. What time is sunset?
7:21.
You guys are supposed to be astronomy students, you're supposed to be aware of these things. Yeah, around 7:20, 7:22, somewhere there. Very good. What time is the moon rise? If it's a full moon, what time does the moon rise?
Like 7.
If it's exactly full, it'll rise at 7:22. If it's full moon, it has to be opposite the sun. So as the sun sets, the moon rises. I used to live, before I moved here, I lived in Georgia, in the mountains of northern Georgia. And in fact, we're right by the highest mountain in Georgia, it's called Rapsdale Hall. And there were these hikers that would like to go up to the mountain and watch the sunset. And they wanted to go up on the day where they could see the sunset and the full moon rising. So they would call me each month and say, which night can we do that? Because I was an astronomer and I would tell them which night was the best night to go up so they could see both of them simultaneously. Which is kind of a cool thing. Around here, it's hard to do because you're not on top of a mountain, you can't look down. You get too many trees and stuff in the way, but it's the same idea. All right, what's tomorrow?
Tuesday,
The what? The autumn equinox, the autumnal equinox, which means what? Yeah, the declination of the sun is 0. Its right ascension is. We covered all this last week.
Yes, we did.
What was it? 12 hours. It's 0 on the vernal equinox, right? So it's 12 hours right ascension, 0 degrees. Is it in the ascending or descending node? Descending, because it's moving to the south. Good. All right. Where does it rise? Set. Exactly. East and west, right? Only on the equinox does it rise and set exactly east-west. Now, a few days either side of it, it seems east and west, you know. But exactly east and west is right on the equinox. All right. Good. Tonight, we're going to talk about time, which is chapter 2 in your book. We're actually going to kind of combine chapters 2, 3, and 4. A lot of stuff, but I covered some of that stuff actually last week. So time, what is time? Change of what?
Time.
You can't use time to define time. What kind of events? Yeah, time between is what? Yeah. What's our fundamental unit of time? Now, where did the second come from?
Where did it come from now, or like? Where did it-
Yeah,
where
why?
did it come from?
What really? That's what we use for our physics fundamental unit. But what is, from a perspective of humans, our fundamental unit?
Well, because didn't the Babylonians 20 seconds? The 60.
Came from the sun to go from 1 minute to.
They like the sun.
That's one part.
You're right. Now you're getting somewhere, right? So the fundamental unit is actually a day. Because to humans, it would be from, depending on what culture you're in, like whether you were Hebrew or Babylonian or Egyptian, some would do days starting at sunset to sunset, some would be sunrise to sunrise. The idea of midnight being the start of our day didn't come till many times later. Because ancient people, they couldn't tell when midnight was, right? Sun's down, sun's up, so the sunrise to sunset was the time, right? And still, like in Hebrew custom, their Passover and stuff starts at sundown and goes till the next sundown. So it doesn't go by our midnight. That was something we created later on. We created it later on because it was actually easier to deal with the day changing at midnight when most people are asleep. That's pretty much why it was. It's just more convenient at that time. Now noon became the most important time for astronomers. Why? Where's the sun at noon? Yeah, it's on the
Yes,
meridian. It's on the meridian. So remember our Herb diagrams from last week. This is the meridian, right? This is east, this is west. Okay. And if you're at a latitude of 30 degrees north, that means that what? And the north celestial pole is how many degrees up here? 30 degrees above the horizon. And then we have this circle, which is the celestial equator. Sorry, that's supposed to be 90 degrees. Celestial equator, which is 90 degrees from the north celestial pole, right? We went through all this last week. In fact, you probably did some of this on your homework, I hope. All right, then where's the sun? Yeah, the sun's a mess, isn't it? Yeah, the sun follows the ecliptic. Remember, the ecliptic goes from 23.5 below to 23.5 above, so it depends on what time of year it is. So, remember our celestial sphere, this diagram with the Earth in the center. Our celestial pole, south celestial pole, celestial equator. The ecliptic is the path of the sun, right? Okay. When's the sun at its highest declination? What day?
Summer solstice.
Summer solstice, and what's the
June 22nd.
okay? And what's the angle?
38 point.
Angle between the declination of the sun. 23.5 degrees, right? Or what that says is this angle between these is 23.5 degrees, right? Where's the sun right now? Yeah, where my drawing really poor. That's supposed to be a circle. Yeah, we know it's going right through the equinox, right? So for us right now, it's really easy. The sun's going to be straight east and straight west, right? But in the winter, where's the sun going to rise? Is it going to rise in the northeast or the southeast? Are you sure?
No, it's gonna be yes.
Yeah, it's the southeast. Trust yourself. You're right. The sun's going to go down here. So on the winter solstice, the sun will make a circle that is at a declination of negative 23.5 degrees. Is it a half circle? No. No. That's why we don't have 12 hours of daylight in the winter solstice. Around here we have roughly 10-ish, 9 something actually, but we don't vary a lot. Why don't we vary a lot? I mean, we get 10, 9.5 hours in winter solstice, we get up to about 14.5 the summer solstice.
We're kind of closer to, we're kind of
Closer to the
equator.
equator. What if you lived on the equator? Do you get longer days and shorter days? But the sun still moves. I mean, the sun moves from here to here for everybody on the earth, right? 47 degrees, 23.5, 23.5, 47-degree change. So how can it still be just 12 hours on the equator?
Because the tilt, with the tilts, you get direct sunlight at the equator.
Where's the north celestial pole if you live on the equator?
It's equal.
Exactly north.
It's exactly north, right? The whole thing rotates down because your angle here becomes 0. Where's the celestial equator?
9 degrees.
Straight up. So actually, the sun goes straight up, straight down. And so, even in the winter, it just moved over a little bit, but it still goes straight up and straight down. It still is exactly half a circle. So it slightly shifts where it is on the horizon. And those that took my archaeoastronomy class, even those places we talked about down in Mexico and southern Mexico, which are at like 12, 14 degrees, it was still moved to different places, but they didn't really have a change of days. They actually really don't have many seasons. When you're on the equator, you don't really have seasons at all. You kind of have like a rainy season and a dry season. And that's pretty much it. There's really no change in the weather. Now, as you get further and further north, what happens? This goes higher and higher. The celestial equator gets lower and lower. And so you start making really big circles. And when you get up to the Arctic Circle, 66.5 degrees latitude, the sun just goes around. On the summer solstice, it never actually sets. You get 24 hours of daylight. Right? Makes sense? So, a solar day. How do we define a solar day? For astronomers, it's from not sun up, sun on the meridian, or what we call local noon, until the sun hits the meridian again. Right, that's our fundamental unit of time. And then we split that into hours, minutes, and seconds, right? Which we probably got from, well, we got it from the Egyptians, probably stole it from the Babylonians. And that's where they were obsessed with the number 60, which is why we ended up with these 60s. And we still do it today. So a solar day is local noon to local noon, or the interval from local noon to local noon. If you're going to measure that on a clock, is that always exactly 24 hours?
No.
Why not? Does the Earth spin faster and slower?
It's slowing down.
Oh yeah, but that's 2 milliseconds every
When
100 years. So you can't function that. I'm talking about just, is it 24 hours
No, because we
long all day, all year long?
revolve around the sun, so it's gonna be different.
Why?
Because in the winter, the days are shorter than.
Well, why would that make any difference? That just means that it's making a smaller path in the sky, right? No, you're on the right track. You guys are right. It isn't the same. Solar days vary. It's tricky, but I want to know why. There's something called the equation of time, which is, it's in your book, but it looks something like this. It's a really weird graph. It looks like this. Yeah, you found it. It's right there. What page is that?
20.
Page 20, the equation of time. What does that plot? Over here is minutes. And this is days of the year.
It is the day numbers, minutes and days numbers on the bottom.
Yeah, exactly. What does that mean? It means that sometimes,
I guess it would be like minutes and then days of the year and everything, right?
Yeah, so sometimes, if you were moving your clock, your watch, which does 24 hours exactly, sometimes the sun's gonna be behind it. Sometimes the sun gets ahead of it, and it varies. There's two reasons. We're on to one, kind of. What is it?
Revolution.
Yeah, but what path do we make around the sun?
A circle.
Are we on a circle?
We're
It's
Elliptical. If we were on a perfect circle, this wouldn't happen, but we're on an elliptical orbit. Remember an elliptical orbit? We learned from a guy named Kepler, right, that all planets go in elliptical orbits. And that at one time, this is a high exaggeration, but here's the sun. We are actually close to being a circle, but we're not a circle. We're about 3 million miles closer when we're close to the sun. Anybody remember what this point was called? Perihelion, good. And aphelion out here. But when you're closest to the sun, what did Kepler's second law say?
Move back.
You move faster. So if you're moving faster here, then as we're spinning around, but moving at the same time, the Earth can't catch up before we moved along. And so our days are actually longer. Essentially, you're moving faster, so you can't catch up as fast when you're spinning. Over here, when we're moving slower, we can catch up faster. So that's one reason. But if it was just one reason, we would have a nice perfect sine curve. For those of you that are math majors or take a math class, right? If it was just that, we would have a perfect sine curve corresponding to perihelion, helium, and aphelion, but it's not. If you've ever done like Fourier analysis, anybody taking math methods? Okay, where you add like sines and cosines together. This is two sine waves added together. You can get that kind of pattern at different periods. You add them together. The other thing that affects the sun is this tilt. Like, why is it tilt? Well, remember the Earth spins parallel to the celestial equator, right? But sometimes the sun is moving up away from the celestial equator. Sometimes it's moving parallel to the celestial equator. Sometimes it's going down. And so you can imagine if it moves that far, well, if it's going down, that's going to, on an angle, that same amount is going to seem like less because it's on an angle than when it's around the summer solstice when it's going parallel. So that will change the length of the days too. So there's two reasons why a solar day is not 24 hours. It varies. And they knew about this, they've known about this for a long time. Even before clocks were invented, you can make sundials that actually compensate for that. You know, by when the sun's at a certain position in the year, it's going to be either ahead or behind, depending on what day of the year it is. And you can create this really cool pattern called an analemma. Has everybody seen it? It's like a figure 8 pattern that the sun actually makes in the sky each year. All right. What is sidereal time? Solar day is told by the sun, right? So what's sidereal time? What does sidereal mean? These Latin terms. It means star. Yeah, nothing too fancy. Sidereal, so this is star time. So you measure time by the stars. So you get a star. You measure when it crosses the meridian, and then the next night you measure when it crosses the meridian again. Is that the same as solar time? Why not? Does the Earth spin faster at night? Slower at night? No, the Earth just keeps spinning, right? It changes, but the change is like, a few seconds every million years or something. It's not a big effect. It does change, but it's a small effect. And they have things called leap seconds every few years. Because they want to keep it exactly synchronized over hundreds of years. And they have to account for the fact that the Earth is spinning slightly slower. Most of it's because the moon is stealing our angular momentum. It's stealing it.
What does it have, what does it do again? Is it getting closer or?
Further away.
Okay.
But as it gets slightly further away, it gets about 2 centimeters per year further away, it actually is slowing us down, stealing our angular momentum. Small effect, but it is an effect. I mean, if you're talking about billions of years, it makes a big difference. 2.5 billion years ago, the day was only about 14 hours long instead of the 24 hours. But you got to remember, life in humans has only been a few thousand years, so especially modern humans, about 10,000 years, that's still trivial in the scheme of things, Earth-wise. All right, so sidereal time is time by stars. And yes, they are different, but why are they different?
Sun doesn't fall.
Sun has rules, just like everything else, right? That's the job of a scientist, is to figure out what the rules are.
Does it matter the season? Like if you're watching the same star?
No. Sidereal time doesn't matter. Sidereal time is way more precise than solar time. Because of that. Sidereal time is essentially exactly measuring the rotation of the Earth. For solar time, you have to take into account the fact that the sun changes. So what happens? Here's the Earth. We have a solar day. Here's Herb, right? Local noon, the sun's right over his head. But by the time he's rotated around once, is the Earth in the same spot?
No.
How far does the Earth move?
A whole day away.
A whole day. How far? How many degrees? About 1 degree, right? 365 days, about 1 degree. So the Earth is now over here. Right here, right? Now, if Herb should be right over his head, right? If Herb is looking at the stars, which are out here some infinite distance away, not looking at the sun, then when Herb is down 360 degrees, the stars are over his head. So when you're doing sidereal time, you're actually measuring when the Earth is spun exactly 360 degrees. When you're doing solar time, you're actually measuring how long it takes to take 361 degrees. Kind of like if you're back there and I'm spinning around, but while I'm spinning, I step over here. I'm looking this way, I've gone 360 degrees, but now the sun's over there, so I have to turn a little bit further to actually catch up to the sun. What's the difference in time between a solar day and a sidereal day? How many minutes? What's that? No, 125. Hey, let's figure it out. All right, how many minutes in a day? 24 times 60. Let's calculate. Sorry, what was that?
1,440.
So there's 1,440 minutes in a day. How many days does it take for the Earth to go around the sun?
1 day.
365, right?
All right. Okay.
So take 1440 divided by 365.
4 minutes.
Yeah, 3.9 something. Yeah, we're gonna round it to 4 minutes. The difference is 4 minutes a day. Now, the confusing thing is when we do clocks, how long is this day? 24 hours, right? How long is sidereal day? 24 hours. But there's 4 minutes difference, which means seconds are not the same. One sidereal second is not the same length as one solar second. Yeah, you're like, why? Why would we do that? Well, nobody else in the world cares about this except for astronomers, because we care about the stars, right? Everybody else cares about the sun, but we care about the stars. 4 minutes a day means that if you watch your star rise, you watch Aldebaran rise at 9:40 p.m., what time is it going to rise tomorrow? If it rose at 9:40 p.m., tomorrow it's going to rise at 9:36. It gets 4 minutes earlier because the sidereal day is 4 minutes shorter. Remember, you have to rotate extra to make a sidereal day. So, to make a solar day. Sidereal days are 4 minutes shorter, which means stars rise 4 minutes earlier every night.
If we use our clock. Right?
Yeah, we're rounding it to 4 minutes. Is that what you're saying?
But no, if we use the strong clock, then it's going to be exactly. the
Yeah,
same
if you use a sidereal clock, yeah. 4 minutes shorter on a solar clock.
time.
Yeah. On a sidereal time day, it would rise. Well, no, it's still going to rise because solar time is when you rise or set. Okay, so it's confusing. Now, some of old observatories, I don't think they do it much nowadays, would actually have clocks that were sidereal clocks on the wall, right next to the solar clock. When would they be the same? Is there any time during the year these would match? Which one? Which equinox would they be exactly the same? The vernal equinox. Remember, we measure everything from the vernal equinox, right? On the vernal equinox, that's where 0 hours is in right ascension. So on the vernal equinox, it's exactly synced up at noon on the vernal equinox. How far are they going to be different tomorrow? How many hours?
Oh, 12 hours?
12 hours. They're going to be exactly 12 hours different. And then by the time we get back to the next vernal equinox, they'll be back in sync again, right? We're exactly halfway from the vernal equinox. All right. Yes. You're like, why do we care about this? Stay with me. Here's Herb. When you have a star, let's say we have a star here, it rises and goes like this, right? The right ascension of a star on the meridian is the local sidereal time. Did you get that? Kind of like local noon is instead of local noon, it's the local sidereal time. So that's why astronomers and observatories would have a sidereal clock, because you could look at the sidereal clock and you would know exactly what right ascension the stars were to look at, because they're right on the meridian, which is the best time to look at. They're highest in the sky. So it's convenient for astronomers. For anybody else, yeah, nobody else even cares, right? But for astronomers, the sidereal time is actually quite important. In fact, we use sidereal time the whole time. Solar time is just confusing. All right, so in a month like September, how many hours earlier does the star rise at the end of the month than at the beginning? 4 times 30 is 120, which is 2 hours. Oh, or we could have said, oh, it's 24 hours in a year. And there's how many months?
Well,
So each month is going to change by 2 hours, because by the time you get to the next year, it has to be back in sync again, right? So yeah, about 2 hours per month earlier. Which is why we have winter constellations, fall constellations, summer constellations, because you're slowly seeing different parts of the sky, because everything keeps rising earlier and earlier. Nothing ever gets later. All right. So, the right ascension of a star on the meridian is the local sidereal time. How fast does the Earth rotate? I want angular velocity. Degrees per hour. 15. Where'd you get that from? Because I told it to you?
You told us. Because you told us to.
Can you figure it out? Yeah, it goes 360 degrees all the way around in how many hours? 24. This is not hard math. 15 degrees an hour. How many degrees a minute? Which is, or the fraction is 1 hour over 60 minutes. The hours cancel, so you get 15 over 60, which is 1/4. Fourth of a degree a minute. Which is how many arc minutes? Now, what's an arc minute?
1/248.
Or 60 arc minutes makes what?
1
degree.
1 degree.
1 degree. No, there's no such thing as an arc hour. All right, and 60 arc seconds make what? 1 arc minute. All right. Should have seen this in another class. Have you seen that, right? Okay. I know if you had my class, you saw it.
How do you get the arc second? It's like, how do you measure it? How do you get it? No, like, yeah, 60 is 1 degree, but how do you get?
We just take a circle, right? You break it into 360 parts. That's a degree. You take each degree, you break it into 60 more parts, you get arc minutes.
Oh, yeah, you go with,
It's just a measurement, right? You break each of those into arc seconds. It gets really, really tiny, but astronomers, we deal in arc seconds all the time. Remember that, because we're going to talk about arc seconds a lot. Because that's really the limit of what you can see in a telescope on the Earth is on arc seconds. Human vision is on the order of arc minutes. We can only separate things down to arc minutes, few arc minutes. Depending on how good your vision is. Some people have better numbers. All right, how big is the sun in the sky?
About half degree.
Yeah, half a degree. So how long does it take to set?
1 degree, half a degree is
2 minutes.
30 arc minutes.
2 minutes. Somebody's paying attention.
No.
I gave you all the information. Here's the sun. It's half a degree across, right? Yeah. So this is half a degree. So by the time the sun moves a half a degree, well, it moves a 1/4 degree in a minute. So 2/4 is a half. So it takes 2 minutes. Now, the reality is that's not the case. Why is that not the case? This would technically only work if you're on the equator when the sun's going straight down. Does the sun go straight down?
No,
What angle does the sun make here? Last week. What angle is the sun going down there?
57.
57, yes.
Parallel to the.
It's always parallel to the
So what's the equator?
less than equator, right? Which is 57 degrees if you remember right, this angle here, 57. So it always goes down at an angle of 57, so it's actually going more like this, so it'll take longer than the 2 minutes. But it's pretty quick, it's quicker than you think.
Isn't it only like 2 minutes? 1/4 in a minute, a half maybe in 2 minutes.
Now think of it, if you're up here at the top of it, right? It's a half a degree away,
Oh, okay, yeah.
so it has to move 2/4 minutes or 2 minutes. Roughly. Now, if you live on the North Pole, it can take weeks for it to go down. Because it just goes around the horizon, so it just barely changes each day. All right. We got this? Remember this? Because we're actually going to do this later when we start talking about telescopes. We're going to use the rotation of the Earth to figure out how big a field of view your eyepiece is. Our telescopes actually track the sky. They rotate exactly the opposite way the Earth is, so they follow the stars. Right? And what rate do they track at? Do they track at sidereal rate or solar rate?
Sidereal.
Sidereal, because we're looking at stars, right? So it has to match the sidereal. That's why astronomers do sidereal time. But if you turn it off, and then you just time how long the star takes to go across, if a star takes 1 minute to go across, how big is your field of view? 1/4 degree. Or we would do in arc minutes, that would be 15 arc minutes. Right?
Uh-huh.
You guys are looking at me like deer headlights or something. Hour angle. Oh, I need that later. Hour angle. Another definition here. Hour angle is how far an object is away from the meridian, east or west of the meridian. Is east negative or positive?
No.
We figured out.
No. Yes.
I ask, is it positive or negative? You can't say yes.
I said east is positive. He was agreeing with me.
Oh, east is positive? Try the other
Okay, west is positive.
one. Which way does the Earth rotate?
East to west.
Actually, the Earth
West
rotates
to
west to
west.
east,
West to east,
but it
otherwise.
means the stars go
East to west.
east to west. So that when they're on the east side, so if we imagine our meridians like this, right? They're over here, they have a negative hour angle. And then they hit the meridian, it's at hour angle of 0. And then they go positive as they go past. Okay, so at sunset tomorrow, what's the hour angle of the sun?
It's 90 to down here.
We're doing right ascension, so it's an hour.
Sunset?
Sunset.
6,
12 hours.
12.
No, but keep trying. Sunset, remember this is east back here, this is west.
12 hours, 6 hours.
Sun's gonna be right there, right, tomorrow. It's gonna be straight west. How far is it from the meridian to here? How many degrees?
90.
90, how many hours is that? 6 hours. Right, 1/4 of a day. So it would be positive 6 hour angle, right? If it's over here, it would be rising, it would be negative 6 hours. Can you have greater than negative 6? Can it be like -8 or 9? Yeah, absolutely. If you're up here, these stars can take more than 9 hours to get to the meridian because they're circumpolar, right? What's the biggest you could be? 12, right? You can be -12 or you can be +12. But that's as big as it can be. Yes. All right. I want you to know this because we talk about hour angle. When we set up the telescopes, I always tell you put it on an hour angle of 0, which means it's pointing what direction?
Directly.
No, so it's
I heard a whole bunch of them.
It's directly with the meridian.
Directly at the meridian, which is
South.
south or north, right? Depends on which way your declination is, but it's going to be on that line, right? Yes, hour angle of 0 is right on that line. Right. Perfect. What's the hour angle of the zenith? 0. What's the hour angle of the north celestial pole? 0. It's right on there, right? Yes. Those points are all on the meridian. Good. What's the hour angle of the sun at local noon? 0. All right. Now, you're going to have a homework. We're going to test your drawing skills. They want you to draw a Herb diagram. But before we'd always put the thing right on the meridian, right? But they're going to say, no, draw it with an hour angle of like +2. So it's not on the meridian anymore.
So you mean, so like where it's like closer to like, it's gonna be, I don't know where it is.
Let's see if we can do that. All right, so we got all this stuff going on here, so we're going to clean it up a little bit. So let's say we have a star of declination 20 degrees. And write it, or an hour angle of +2 hours. Where would I draw that on my Earth diagram? I should ask, where would I draw it on there? Not where you guys want to draw it.
So are you saying that like on an hour angle? Never mind.
What?
Wait,
2 hours from the meridian.
Towards us.
West.
Where does everything rotate about?
the
Nothing,
north
just
celestial.
And how many degrees per hour? 15. All right, we're getting it right. So if I drew a line actually like this, I'm messing with you, right? I don't know if I had enough there, but there should be 6 of those between the meridian and straight west, right? Where each of those is an hour,
Oh, yeah.
right?
Oh, yeah.
So you can think of these as kind of like sticking out of the board, right?
Like the globe.
Yeah, kind of like this. Okay, so if it's here, it has an hour angle of 0. If it was on this one, it would have an hour angle of 2. But what's its declination?
The declination is how far it is from the celestial equator.
So my declination is 20, so where am I going to put it? So the star is going to be right about here. So that if I draw this line, that angle is 20 degrees. And this angle in here is 30 degrees. Because there's 15 degrees per hour.
Oh, yeah, oh, yeah.
And it's 2 hours off, right? The challenge is not can you put it figured out in your mind, but you have to go draw it. And I've seen some of your drawings, you got this 3D drawings kind of fall apart, so take some time, make it good. All right.
Didn't hold back.
So this star would actually make a whole loop like this, right? But at this point, it's right here, right? Now we'll see if you learned anything today. The right ascension of the star is 18 hours, 40 minutes. What's the sidereal time?
18 hours, 40 minutes, so it's the same. Right, we are on
That's what the star's right ascension is.
18 hours and 40 minutes.
Yeah.
Is the local side here?
No. But thanks for playing.
8:40.
No.
What was the question? What was the question again?
Would it be 18
Oh,
hours?
is this there?
I'm trying.
The
You would-
star
you
has,
would
this is the
multiply-
star,
You
right?
would multiply it by like how many months it went by the 4 minutes that you have to take off.
Oh,
because-
that would be way too complicated, but you could do that,
Okay.
but we're not doing that. There's a way easier way.
What are you trying to find?
There is, if you look at your book, there's these huge long equations. I'm not gonna make you do them because nowadays you plug this all into your calculator and it spits it out, or on the internet, you just say, calculate the sidereal time for this star, and it'll just do it, right? So I don't want to waste your time, but I want you to understand.
What is the question again?
The question is, what is the local sidereal time when this star is at an hour angle of 2?
Oh, oh, we did it, right? Okay.
Oh. It's 20 hours.
No, but you're closer. Oh, actually, hold it. What did you say?
20 hours?
Yes.
Okay.
Sorry, I didn't hear you. How do you know that?
Because the RA of the star is at the meridian, is the local sidereal time of the meridian.
Right, so
you add it to those.
we need to know what the RA of the meridian is.
Yeah.
But we know that the star is over here,
Yeah.
2 hours past it. So if this was 18, this would be 19, this would be 20 hours and 40 minutes. And it just keeps changing all night long, right? Just like a clock. Good, that's what I wanted you to get. It took us a while to get there, but we got there. All right, and we talked a little bit about this last. Oh, 2 more things. Julian date. What's Julian date? Really big numbers, you're right. Julian date is another thing astronomers do. Because let's say you are calculating, you're watching a variable star that gets really bright every 500 days or something like that. Well, if you say, oh, I want to know when it was bright 30 years ago, it gets really hard to figure out because you have to worry about how many years and then how many of those years were leap years. And so it's very confusing. The easiest thing is to steal what the Mayans did. They have a calendar, which all you do is count every day, and it just gets bigger by 1 day every day. Skip the whole years and months thing. That's what the Julian date is. It's just days. And so then you can say, okay, whatever that date is, you just subtract it and you know exactly when 500 days and 500 days was before that. And you can figure out if something's like happening on a regular period. So for astronomers, we use Julian date because it makes way more sense than to use calendar days. Our Gregorian calendar is all messed up anyway. So we use Julian date. Astronomers do that. And we do it in decimals too. You don't do it in hours and minutes. It's going to be day number, well, I don't know what they're at now. They're like day 1,947,7.34987, and it goes up by that. You don't even go up seconds You do it in tens, hundreds, thousands of days, you do decimal dates. It just makes more sense. It's kind of like more of a logical system, way logical system compared to what we have now. And I just wanted you to know that we don't do much with that next class, but if you do any kind of like astronomical research or anything, you will run into the term Julian date. They do that a lot. It also works too, because you can say Julian date, then other people don't have to figure out, well, when was that, how was that, they can just look that up really easy. And to predict things in the future. You'll have to actually hold it. I do have it here, or close. September 13th, 2010, so was that 11 years ago? We were on Julian date 2,455,453. So we're about 20,000 ahead of that now. 365 times 10, about 3,000 ahead of that now. So you can look that up again. There are calculators you can put on the internet to say, what's the current Julian date? And it'll give you exactly, or whenever time it is. You just calculate that. Last thing we want to talk about is, when is the best right ascension for viewing? We talked about this last week. If you want to go observe an object, you want to watch it all night long. It's best when the right ascension of the object is what? I do research on asteroids. And when I decide what asteroid to go study, I want that asteroid to be where compared to the sun? Opposite the sun, right? I want it to rise just as the sun sets, and then it's up all night long, and then it sets just as the sun rises. That is the optimum time, because then you get all night of a viewing. If it's like halfway, if it's on the meridian as the sun sets, you only get it for a few hours. 6 at the most usually. Where if it's up all night long, especially at this time of year, you can get 12 hours out of it because you get 12-hour nights. In the winter, you can even get more than that, right? Sun comes up later. So best viewing, already for viewing, is always opposite the sun. Okay? Now, remember, this is the vernal equinox. What was the right ascension here? 0 hours. Summer solstice? 6 hours. Autumnal equinox. And winter solstice. Okay, but tonight we want to go out and we want to observe. We don't want to spend all night. We want to just observe right after sunset. What would be the best right ascension then? Where's the sun?
It's just.
The right ascension of the sun is 12 right now, right? Okay. So best viewing, remember, is always when it's on the. No, not if you're going all night long, you want it opposite, but if you want to just look at it right away, you want it on the meridian. Because that's when everything is highest in the sky, right? So what's the right ascension of the meridian right at sunset?
6 hours.
No, that's the hour angle of the sun. Of the sun. What is the right ascension? Yeah, it's gonna be 12 plus 6, 18 hours. So you look at something that has a right ascension of 18 hours. There's a star that has a right ascension close to 18 hours. Anybody know what it is? No, different star. I just made that up, but it's the star that we use for our magnitude scale standard. No? Vega. Vega is at about 18 hours. So right now, when we go out and the sun sets, Vega will be very close to being right on the meridian. Roughly. Okay. Also, what's the sidereal time at sunset?
Is, exactly the same.
Yes, 18 hours, right? Because that's the meridian, right? Central meridian is the sidereal time. I have a feeling this isn't going in at all. I'm trying to tie all this together. You guys are like, it's just going right over your heads.
It only takes some time.
Yeah. It is, and you gotta really be good at spatially thinking three-dimensionally, keeping that all in your head. Kind of tricky. But all these things do tie together. All right, I think I covered all the good stuff you needed to know. So, for your homework.
Clarify from the right assumption of the meridian is the local sidereal.
Correct. Right ascension of the southern meridian.
Okay.
You want to be really picky, because if you say, oh, but what about over here? Well, that's technically 12 hours out. So don't go past the north celestial pole. Anywhere on there, you are okay.
Okay.
I didn't mention that because you have to be really picky, but I want to be precise. Homework number
2.
the observatory. Make sure you bring an observing sheet. I didn't give you some. Did I give you some?
Yes.
Okay. You're gonna have to fill it out. And remember, there are no facilities at the observatory, so if you need to use the bathroom, go before you go out there. And I will see you out there in 10 minutes or so. Just get out there, we'll meet up and start working. Oh, I forgot to talk about, we'll talk about that.
July? Yeah, he does think that.